Okay, so we're actually restarting this, so some stuff is already drawn in. We have our initial vectors in white. We have our resultants, because we're heading home, is pointed back towards origin, not the other way. That's in red. And we're now looking at our first vector and breaking that down. We're resolving that vector into its component pieces. So dx1 is equal to sine of 20 times 1.45 km. So dx1 is 0.4959, etc. km, and dx1 is going that direction. Okay, and you can see that from your picture. The picture gives you a visual cue on that. So dy1, because it's adjacent to that 20 degrees, geez, Moser, get it right, is the cosine of 20 times 1.45 km. So dy1 is 1.36255, etc. km, and dy1 is upward. It's in an upward direction. One nice thing also that having the picture there does for you, if you've got it relatively to scale, you also have a visual cue that dy1 should be a good bit bigger than dx1. Because if you look at that picture, you see the magnitude, oh, dy1 in the picture that I drew is over twice dx1's length. Well, that's what we get numerically too, so that's helpful. Okay, now let's go on to our second little vector and resolving it. Okay, so we have our second little vector in blue, and we've got dx2 and dy2. And again, I'm going to pull the little triangle out over here just to assist my feeble little brain, and this is very badly drawn in terms of scale, but try to improve it a little bit. So that's a 32-degree angle in there, and this is 1.37 km. There's our dx2, dy2. Okay, so because dy2 is opposite the angle, we know that the sine, we know that dy2 is going to be equal to sine of 32 times 1.37. So dy2 equals 0.7259, etc. kilometers, and dy2 is down. It's in opposition to dy1. They're running in opposite directions. Okay, and because dx2 is adjacent to that angle, dx2 is going to be equal to the cosine of 32 times 1.37 km. dx2 is 1.1618, etc. km, and it's heading the same direction as dx1 is. Okay, so at this point we're actually ready to start looking at our overall triangle. And I'm going to do the same thing for that I did for these two. Alright, so I've redrawn my little triangle here. And if we look at it, now the tricky part is that the vector it seems backwards to us because it's the going home vector, not the displacement vector. So that's the only reason that the arrow on the resultant, and here's your resultant, is pointing in the direction that it is, because this is the going home vector. Your overall displacements here are still the same. You know, your y and your x are the same no matter how you cut it. So to find our dx total, we're going to take, I should change colors. We're going to take dx1 plus dx2. And what we have to remember is that they are both in this direction. Okay? So because they're both in the same direction, it makes our life easy. We don't have to think about subtracting one or making one negative. We just add them. It's very straightforward. So what we get when we add those for our dx total is 1.6575, etc. kilometers that away, or west. Okay, so now we're going to do our dy total. Okay, so now we're going to find our dy total. Dy total is, of course, dy1 plus dy2. Now, here's the critical piece. dy2 is south, dy1 is north. Now you know that if you look at this, your overall displacement is to the north on the y-axis, so it makes the most sense to make this your positive. Then it's just your larger number is positive and you're subtracting your smaller. So if you do that, you get a dy total of 0.6365, etc. km, and that is north. It's hard to see on the edge there. Okay, we're going to have to shrink a bunch of stuff to get into our next set of calculations. Okay, so we just micro shrunk our dx d1. Okay, so now to the real work. The resultant displacement is the square root of dx total squared plus dy total squared. Resultant displacement. We've got our resultant displacement magnitude is 1.7757, etc., kilometers. To find theta, this is the tricky part because of the fact that it's the going home tangent, not the overall displacement tangent. So we're looking for this angle, and it would be east of south. If you did it the other way, you got a north of west or west of north because you were heading that direction. So you were measuring the angle from the other side. So this is going to be an east of south angle, and it's the inverse tangent function opposite over adjacent of our dx total is our opposite, dxt over dyt. So we get a theta of 68.99, etc. degrees. So this comes out to 1.78 kilometers at 69 east of south. That's really tough to read. So, final answer, 1.78 kilometers at 69.0 degrees east of south. You could, of course, use 21 south of east, same heading. That would be if you were finding that angle, and it would be south of east. That seems straightforward. Okay, so to re-examine that resultant area, if we look at it from the perspective, if we ignore the fact that it was going home, we just look for displacement overall. Is that your question?
I just wanted to see it.
Okay, so if we look at the resultant triangle, whether it's going home or your overall displacement, this is still your total x displacement. Okay, this is still your total y displacement, and this line is still your resultant. Now, if we look at it as just your resultant displacement, where you ended up from where you started, then we would put an arrow here, which is how we traditionally draw resultants, from the tail of the first to the head of the second. If we think about it in terms of, hey, how do I get home from here? Then we just put that arrow on the other end, because we're pointing back towards where we started from. Does that make sense? Okay, 2 is fairly straightforward. You head due west for 4.5 meters, and then you turn, and you go at 35 west of north for 5 meters. And so we want your resultant displacement. So that's just going to be that line right there. This is your resultant displacement. So, as always, we have to break it apart, and pretty good job there. So there is our...
Please excuse me.
So we have in that first vector, it's all x. dy1 is 0, which makes our lives easier. So dx1 is the whole darn thing, for 4.5 meters. dy1 is 0 meters. Now in the second one, of course, we're not so lucky. We couldn't be that lucky twice. So we've got that, and we've got that. And of course, that displacement is heading that direction, that one, that. What did I do that makes life harder? Yeah, I took the outside. Because it's easier to visualize that way. But let's keep it simple as we have been attempting to. Okay. All right. So, if we look at that second vector, this is our dx2, and here's our dy2. And it does get a little bit crowded. I mean, that's one argument for drawing it outside. Just remember that once you find the magnitude of those lines, you can move them parallel to themselves. You can always move them parallel to themselves. Okay, so dx2 is going to, it's opposite our angle, so it's the sine of 35 times 5 meters. And dx2 is 2.867, etc. meters. dy2 is adjacent to our angle, so it's going to be cosine of 35 times 5 meters. And dy2 is 4.09576 meters. Okay, so that's easy, relatively. Now we need to find our total x and y displacement. Well, resultant vector overall, there is the total x displacement, there's your total y displacement. So dx total, dy total. Okay, so we know that dx total is equal to dx1 plus dx2. So dx total is equal to 4.5 meters plus 2.867, etc. We get a dx total of 7.36788, etc. meters. And dy total is equal to dy1 plus dy2, and of course dy1 is 0. So dy total is just actually equal to 4.095, etc. meters. Okay, so now you've got a triangle with your overall x, 7.36, etc., and your overall y, 4.09, etc. Badly drawn. So we know that dr is equal, so we know that the resultant displacement, our dr here, is equal to the square root of dx total squared plus dy total squared. Okay, plug in numbers, we get a resultant of 8.4297651 meters. And if we want to find this angle, which we do, we can use an inverse tangent function. dy total is our opposite. dx total is our adjacent. Tan minus 1 of dy total over dx total. Theta is equal to 69.0, and I'm going straight to the, oops, that's the wrong problem I'm looking at. Okay. 29.06, etc. So it sig figs out to 29 degrees. 29 degrees north of west, because we're looking at that angle. So final answer, 8.4 meters at 29 north of west. Okay, you can do this angle, and then it would be, what, 61? Yeah, 61 west of north. But either way. Clear on that? Level of comfort with that one now that you saw it done? Okay. Okay, we'll finish number 3 tomorrow in the video, so that's it for today.